Greetings, Panthers. This is Dr. Augustine. How are you all doing today? Today we're going to take a look at the difference between KSP and solubility. This is actually the second video, part 2 of part 3 video series. This covers chapter 17.6 intro. And the first video, we introduced the idea of KSP, and we did a couple of calculations showing how you can find this equilibrium constant related to the solubility of solids. And we also related how that compares to the solubility rules that you learned way back in chapter 4 in General Chemistry 1. So the name has the word solubility in it, so you might wonder how KSP is related to solubility, because we've also defined solubility earlier in the semester as the amount of stuff that will dissolve in some amount of liquid, like for instance, how many grams of a solid would dissolve in a liquid before you hit the solubility limit, or you, in other words, reach a saturated solution. So KSP and solubility are related to each other, but they're not the same thing. So this is a good time to clarify what the difference between these two things are. So KSP is called the solubility product constant, and it's actually an equilibrium constant, which is distinct. Okay, so equilibrium constants, we know, based on the name, are constant, and that is at a given temperature. So if you're, let's say, operating at 25 degrees C, no matter what conditions you have your sample under, KSP will always be the same. Doesn't matter what the solution is, doesn't matter anything, KSP is going to be a constant at a given temperature. So if you're at 25 degrees C and you're given a value for KSP, that will be true no matter what your conditions are. Solubility, on the other hand, is highly dependent on the solution. So solubility is the maximum amount of material that can dissolve under a given set of conditions. Okay, so this is a key distinction. Depending on what the conditions are, the solubility in grams per liter or in moles per liter, those are the kind of typical units, grams per liter, moles per liter, that can vary a lot. And we're actually going to spend the end of this video and the beginning of the next video to tell you the conditions under which the solubility can change dramatically. All right, so here's the key idea then. Solubility is highly dependent on the solution conditions, and it can actually vary by orders of magnitude. Factors of 10, 100, 1,000 is not uncommon for solubility under different solution conditions. KSP has only one value at a given temperature. So if we're at 25 degrees C and you look up the KSP value, that's what it's going to be no matter what the solution conditions are. So KSP is really a more kind of generic way of determining solubilities, but it's kind of less intuitive. Solubility makes more sense. You know, so many grams will dissolve in a liter of solution, or so many moles will dissolve in a liter of solution. But the conditions that the solution is under will highly determine what the solubility is. So it turns out there's 3 factors which profoundly affect the solubility, called the common ion effect, the effect of pH, and what's called a complex ion. So in this video, we're going to do a problem just calculating what the solubility is, or sort of defining what solubility is. Then we're going to take a look at the common ion effect. In the next video, the third video in this series, we'll look at the effect of pH, and we'll also look at the effect of formation of a complex ion. Okay? So let's take a look at an example solubility problem. So this is not a KSP problem, this is a solubility problem. And the way you solve these are basically going to be the same no matter what you have, except depending on the solution condition will depend on what the solubility is, as you'll see in a second. Okay, so here's an example. KSP for calcium fluoride, we're given the molecular weight, is 3.9 times 10 to the minus 11 at 25 degrees C. Remember, the temperature does impact the equilibrium constant. Any equilibrium constant is impacted by KSP. So we want to calculate the solubility of calcium fluoride in grams per liter. Now, recall I said there's a couple different units that are common. Grams per liter is one of the common ones, and moles per liter is the other common one. So this particular problem is interested in grams per liter. Okay, so how do we set up pretty much every chemistry problem we have? We start by writing out a balanced equation. So let's write the equation for the dissolution of calcium fluoride, CaF2. This is an equilibrium problem. It's going to break up into calcium ions, and it's going to break up into 2 fluoride ions. So this is a stoichiometry problem from Gen Chem 1. CaF2 will break up into 1 calcium ion and 2 fluoride ions. And then we're going to set up an ice table. We're not concerned with the solid on this equation because that doesn't get included in KSP, but we are definitely concerned with these ions. So my ice table, I'm going to have 0 of calcium to begin with, 0 of fluoride to begin with, and TRO uses S, so we'll just be consistent with TRO. So this is going to go up by S. This one is going to go up by 2S. Okay, this is going to be a little bit different from the acid-base reactions that we've had. Those have always been plus X or minus X, but this one's going to go up by 2S, and the reason is for every one of these that gets formed, every 1 calcium ion, 2 fluoride ion gets formed. That's from the stoichiometry. So for every 1 S of calcium ions, we need 2S of fluoride ions that get formed. And then, of course, my equilibrium value is going to be S and 2S. All right? You've done a whole lot of equilibrium problems, so you probably know where we're going next with this. We're going to write the KSP expression. KSP is equal to 3.9 times 10 to the minus 11, and that is equal to the concentration of calcium ions times the concentration of fluoride ions, the whole quantity squared. All right, so 3.9 times 10 to the minus 11 is equal to S times 2S squared. Note, this is a really common place for students to make a mistake. They forget to square this 2, they forget to square this S, okay? This entire quantity is squared. So we need to square this quantity, and then we need to multiply it by that S. All right, so 3.9 times 10 to the minus 11 is equal to 4S cubed. Again, this is a common mistake that students make. They forget to square this entire term, so either they don't end up with 4S cubed on this side. If you don't end up with 4S cubed, then obviously the answer is not going to be correct. Okay, divide the 4 over, so we're going to have S cubed is equal to 9.75 times 10 to the minus 12. We're going to take the cube root of both sides. And we're going to have S is equal to 2.1 times 10 to the minus 4. And this is actually moles calcium ion per liter of solution. Okay, it's a molarity unit, but the key is this is actually moles of calcium ion, because remember, S is related to the calcium ion concentration. Okay, so 2.1 times 10 to the minus 4 is my concentration, my molar concentration of calcium ions, but the question's really asking for solubility of calcium fluoride. Okay, so we're almost there, but we're not quite there. And it's also asking for grams per liter. It's not asking for moles per liter. So I need to do a little bit of stoichiometry to turn this from moles calcium ion into grams of calcium fluoride. All right, so let's rewrite this. 2.1 times 10 to the minus 4 moles Ca2 plus per liter, 1 liter of solution, times 1 mole CaF2 for every 1 mole Ca2 plus. That's from the balanced equation, right? We've got 1 mole of calcium ions for every 1 mole of Ca2 plus. I'm going to cross these units out. And then I'm going to multiply by the molar mass because it's asking in grams per liter, not in moles per liter. So now I need 78.1 grams CaF2 for every 1 mole of CaF2. That's going to cancel that. And then when we multiply these out, I end up with 1.6 times 10 to the minus 2 grams CaF2 per 1 liter of solution. Okay, and that's the answer. That's how you solve the solubility. That's how you find the solubility of calcium fluoride given the KSP. So the type of problem is we were given the KSP. We're asked to find the solubility in so many grams per liter. Okay, if this was in moles per liter, the answer would have been this would have been the answer. We would have one more step. We would have needed to say times 1 mole CaF2 per 1 mole of Ca2 plus. Okay, so it would have been 2.1 times 10 to the minus 4 would have been the moles per liter solubility, and the grams per liter is 1.6 times 10 to the minus 2 grams per liter. Okay, so the solubility problem is quite straightforward. It's an ice table. We're given KSP. We start with 0 of each of these. We add S, that's the amount that's dissolved. Remember 2S, that's based on the stoichiometry. And then we got to remember to carry that through when we write out the KSP expression. Pretty straightforward based on our prior knowledge of equilibrium problems. Now, let's take a look at the factors that affect the solubility, because this is true for a solution that's just the solid dissolving in water. What happens if we're not just dissolving it in water? What happens if we have some other ions in there? And the first one we're going to take a look at is called the common ion effect. And what the common ion effect means is what happens if one of these ions is already dissolved in solution. So we'll take a look at that next. All right, so what happens to the solubilities is you get a massive drop in the solubility if you have some other common ion dissolved in. So here's a plot of one particular thing, and this is calcium fluoride. Every one of our examples is going to be calcium fluoride. This is the molar solubility of calcium fluoride. So remember, we just calculated what the molar solubility was. It was 2 × 10⁻⁴ if we have pure water. But here's a plot if we have some concentration of sodium fluoride. In other words, if we're trying to dissolve calcium fluoride in an existing sodium fluoride solution. So if we go from 0 to 0.05 molar, which is not a very high concentration, the solubility drops by nearly 4 orders of magnitude. That's a factor of 10,000 drop in solubility. And of course, as we keep increasing the concentration of sodium fluoride, the solubility continues to drop. The KSP is not changed. Okay, that's a constant. But the solubility is radically different if we are in a solution of something that contains a common ion. The fluoride is the common ion. Okay? So that's the idea behind the common ion effect. Now, if you want to understand why that is, let's take a second and write out the equation to understand this. So CaF2 solid equilibrium with Ca2 plus aqueous plus F2F minus aqueous. And if we think about this solution right here, we got sodium fluoride, so this is NaF aqueous. And what that implies, you know, if it's an aqueous already, it means we have Na plus ions plus fluoride ions in solution. All right, so if we already have an existing solution with fluoride ions in it, that means there's some of this already. And what do we know from Le Chatelier's principle? If we have some of the products already existing, what that's going to do is it's going to drive the reaction back towards the reactant side. Okay, so if we have existing fluoride ions, Le Chatelier's principle in an equilibrium, Le Chatelier's principle tells us it's going to be pushed away from this towards the other side of the reaction, which is the solid form. So we anticipate that less calcium fluoride will actually dissolve since we have existing fluoride ions in solution. Okay, we can understand this graph strictly in terms of Le Chatelier's principle. We have extra fluoride ions. It's going to shift the equilibrium away from the formation of the ions and towards the solid side. But let's do this in a more quantitative way using the problem down below. All right, so look at the problem. KSP for calcium fluoride, molecular weight, blah, 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 is 3.9 × 10⁻11. It's exactly the same setup as the last problem. Calculate the molar solubility, so now we want moles per liter of calcium fluoride in a solution that is 0.01 molar in sodium fluoride. Okay, so now we have a solution that has an existing concentration of sodium fluoride, but essentially it's the exact same problem we just had. So let's take a look at this. All right, so we're going to do the exact same ice table that we did before, except now we need to have an existing initial concentration of fluoride ions. That's coming from the sodium fluoride. Now, if you're wondering where the 0.1 molar is coming from, remember NaF aqueous dissociates into Na plus aqueous plus F minus aqueous. And if we have 0.01 molar of sodium fluoride, this is in a 1-to-1 ratio. It means we also have 0.01 molar of sodium ions and 0.01 molar of fluoride ions. So that gets put into the initial concentration of fluoride ions. Now, this one's going to go up by S. This one is still going to go up by 2S. They're in a 2-to-1 ratio. So my equilibrium concentration is going to be S and 0.01 plus 2S. So now we'll write our KSP expression. KSP equals 3.9 times 10⁻11. It's equal to the concentration of calcium ions plus the concentration of fluoride ions squared. And so that's going to be equal to S times 0.10 plus 2S, whole thing squared, and that's going to equal to 3.9 times 10 to the minus 11. All right, now if you look at this, based on your knowledge of equilibrium expressions, you know that this number, 10 to the minus 2, is way, 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 way bigger than 10 to the minus 11. So this 2s is going to be really insignificant compared to the 0.01. So we're definitely going to be able to make the approximation in this case. The only time you can't make the approximation is if this number is close to that number. If this was 10 to the minus 2 and this is 10 to the minus 3 or 10 to the minus 4 maybe, you're going to need to do the quadratic formula. But in this case, 10 to the minus 2 and 10 to the minus 11, 100%, you do not need to worry about that 2s. All right, so let's rewrite it with the approximation. 3.9 times 10 to the minus 11 is approximately equal to s times 0.010 whole quantity squared. If we do this calculation, we get s equals to 3.9 times 10 to the minus 7 moles Ca2 plus per 1 liter. Okay, now, again, this problem is asking for molar solubility of calcium fluoride, not molar solubility of calcium ion. So we do need to do one more step just to make this complete. They are in a 1-to-1 ratio, but technically you need to say times 1 mole CaF2 for every 1 mole Ca2 plus. That cancels that. So our solubility is equal to 3.9 times 10 to the minus 7 moles CaF2 per 1 liter. That is our solubility under the conditions that we have a 0.1 molar fluoride ion solution. All right, if you remember from the last problem, that we did, it was 2.1 times 10 to the minus 4 molar. Okay, so check this out. You have a 3 order of magnitude difference in solubility by just having a 0.01 molar solution of sodium fluoride. So this is way less soluble. This current situation is way less soluble than if we were just doing it in pure water. And that's exactly what this graph is saying. If you have pure water, it's up around 10 to the minus 4. As we start adding solution, we get a big, big, big drop in solubility. So the KSP hasn't changed. Okay, that is a constant. It's the same temperature, 25 degrees C, but the solubility has dropped by a factor of 1,000. Okay, so really big deal. Solubility is not the same thing as KSP. Solubility is highly dependent on the solution conditions. In this case, if we have a common ion, which is the fluoride ion, we're going to get a big drop in solubility. Let's take a look at one more problem and see how this is influenced. All right, we're going to take a look at another example of a common ion effect, and I'm going to have you, maybe a good thing for you to do would be to just try doing this yourself before I do it. So stop the video, take a look at it, and see if you can figure it out yourself. It's the exact same problem as the last one, essentially, except we got a slight difference now. KSP is 3.9 times 10 to the minus 11, so this is exactly the same setup. Calculate the molar solubility, exactly the same, of calcium fluoride in a solution that is 0.01 molar in calcium nitrate. So just a slightly different solution that it's dissolved in. Let's see how the solubility is affected. You should be able to do this on your own, modeled after the last one. Okay, I'm trying to save a little bit of time here, but our calcium nitrate aqueous solution breaks up into calcium ions plus nitrate ions. If we have a 0.01 molar solution of calcium nitrate, I'm going to have 0.01 molar of calcium. They're in a 1-to-1 ratio, and I'm going to have a 0.02 molar of nitrate. They're in a 2-to-1 ratio, 2 moles of nitrate for every 1 moles of calcium nitrate. Okay, and of course, in my actual calcium fluoride, which is what I'm trying to find the solubility for, I need to plug in the calcium ion concentration as my initial concentration. Okay, so I've filled out the ICE table. Hopefully you have something that looks like this. 0.10 is my initial concentration of calcium ions. I have 0 fluoride ions initially. This goes up by S. Fluoride goes up by 2S. So 0.01 plus S, and then 2S is my final equilibrium concentration of fluoride ions. Same KSP expression that we've had 3 times now. And it's 0.01 plus S times 2S quantity squared equals to 3.9 times 10 to the minus 11. Okay? And so this is, once again, 10 to the minus 11 is much, much bigger than that, so we can make our favorite approximation that we've made so many times before. And I'll just remind you again, this is 2s, the whole quantity squared. Do not forget to square both the 2 and the s. That's a common mistake that students make. So this can be 4s squared is equal to 3.9 times 10 to the minus 11. So S is going to equal to 3.1 times 10 to the minus 5 molar. Okay, so 10 to the minus 5 molar for this case where we have a 10th molar of calcium ions. So you might be asking yourself, how come in the last problem we also had a 10th molar of sodium fluoride? Why was it 10 to the minus 7 molarity for the last problem, and this one is only 10 to the minus 5? Why is it different? Well, the difference is because the calcium ion is only being raised to the 1 power, whereas the fluoride ion is being squared in this KSP expression. So if you have something that's squared or cubed or something to the 4th power, in other words, the coefficient out in front of one of these is not 1, but is squared or cubed or something, it's going to have a much, much bigger effect on the solubility. Even with the exact same concentration, we have 2 orders of magnitude lower solubility with the fluoride case than we do with the calcium ion case. Okay, so if you're having to predict which one of these is going to have a bigger impact, look for the one that has a coefficient out in front. If you have a 2 or a 3 or a 4 or something like that, it's going to have a huge impact on the solubility because that gets raised to that power in the KSP expression. Okay, that takes care of the common ion effect. Next video is going to take a look at the effect of pH, and we'll briefly mention the formation of a complex ion. We'll spend most of our time on pH, understanding how that affects the solubility, because again, the pH has a profound impact on the solubility.